see, I have an innate fear of spiders too, but I captured this one,
Yeah.
so that's kind of
You didn't touch
lower
it.
that
You didn't
fear.
touch it, did you? Like to get it in there?
No.
It just.
Use the meter stick.
Gotcha. All right, before we start our next section today, are there any homework problems that you guys want to go over? I know we've been talking about derivative shortcuts like product rule, quotient rule, and they seem to be going well in here together. I'm just curious how they're going when you try them on your own. Okay, are there any ones? Yes?
You do 12 on 158.
158, yes. All right. Find the equation of a tangent line to that graph at that point, or at that spot. Okay, so we know we need a point and a slope. Let's tackle perhaps the derivative first. All right, so taking a look at your equation, we have tangent times sine. So how are you going to find the derivative? Think about your shortcuts.
That's fine. Sure. Yep. Okay.
What do you guys want to try? Product rule, 1d2 plus 2d1. All right, so 1, and then we need d2, the derivative of sine. Be cosine. Then we're going to add 2, and then d1, the derivative of tangent, one of our newer ones. Secant squared, good. Okay, so there's our derivative. You want to leave it like that, or do you want to try to clean it up a bit? I think that's okay. If that, we can do that the way it is. Let's check out point, and then slope. So to find the point, we're going to plug in pi over 4 into the original function. So you got to think about your unit circle. Pi over 4 is in the first quadrant, so we need to know these values. Okay, so we know tangent is sine over cosine. At the pi over 4 spot, what are the sine and cosine values? Pi over 4 is like 45 degrees. So both of them are square root of 2 over 2, right? So tangent, if you took square root of 2 over 2 divided by square root of 2 over 2, what would you get? 1. Okay, so tangent of pi over 4 is 1. And we just said the sine value was square root of 2 over 2. So when we multiply those together, we're going to get square root of 2 over 2. All right, there's our point value. Now let's plug pi over 4 into the derivative. So tangent of pi over 4 times cosine of pi over 4 plus sine of pi over 4 times secant squared of pi over 4. All right, so we just said tangent of pi over 4 was 1. Cosine of pi over 4 was square root of 2 over 2. Sine of pi over 4 was another square root of 2 over 2. What about secant, though? Can we rewrite secant as a sine or a cosine expression? Secant is 1 over cosine. Okay, so we know the cosine value at pi over 4 is square root of 2 over 2, but we have to square that because it's secant squared. All right, so if we clean it up, all right, square square root of 2 over 2 squared. If we do each one individually to square it, square root of 2 squared would cancel out the square roots, so we're left with a 2. And then the denominator 2 squared would give us 4. What about 1 over 2 divided by 4? 2 divided by 4 is a half, so what's 1 divided by a half? How many times does a half go into 1? 2 times. Okay. So that crazy complex fraction simplifies to 2. And notice how the 2's would cancel in our second term. So we're just left with the square root of 2. How'd it go? Okay. So it looks like our point is square root of 2 over 2 plus another square root of 2. We'll leave it like that. So do you guys think you can go from there now that you have your point and your slope? Write your equation. Any other ones you guys want to check out? No? Alrighty, let's go ahead and check out page 159. So up to this point, in terms of our derivative shortcuts, we've had power rule, we've had product rule, we've had quotient rule, and we talked about the trig shortcuts for their derivatives. We're going to add another one to the list. Okay, we're just going to keep talking about shortcut, 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 because there's going to be a lot of them, but I think you guys would rather do those than the whole limit idea, right? Okay, so we're going to have another derivative shortcut today. I don't want to give it away because this is kind of one of my favorite shortcuts, so I hope you guys like it too. Let's just go ahead and check out this easy example, and then we're going to try to talk about, well, why do we have this other shortcut? Why is this one important? It's eventually going to be referred to as the chain rule, and I'll use an analogy to hopefully make that make sense for us. But let's just check out the first one. Rewrite the function as a polynomial form. Okay, no parentheses, no roots, no fractions. So if you were to technically write 2x plus 3 times and go through a bunch of distribution to get rid of those parentheses, I want you to see what you would get back as your polynomial. Do you guys think you can do that? I think you can. Go ahead and do it. I'm not going to talk through it. I'll show my work, but I think you guys can do that. Mm-hmm. That cubic function look about right? Okay. So if that's the original function just expanded, okay, can we find the derivative now pretty easily using a shortcut, our power rule? We'd get 24x squared plus 72x plus 54. Sound about right? Okay, hopefully that's nothing new to us. Okay, we talked about how if you're dealing with a polynomial, you can expand it and then simplify to help you find the derivative. Let me ask you this though. What if I were to take that same 2x plus 3 quantity and instead of a power of 3, I changed it to 100? Would you guys really want to do the same process we just did?
Nope.
No, I wouldn't either, okay? So realize that it still would be possible to do that though. It would just take you a very, very long time, which means we would eventually get a polynomial which we could then eventually figure out the derivative of, okay? So there is a derivative that does exist, even though it's a crazy high power, but we just can't do it with the techniques or shortcuts we've discussed right now, okay? This is where our new shortcut's going to come into play called a chain rule, okay? So a chain rule is specifically used for composite functions. This is where like one function is put inside of another one. Could you guys understand, at least if this was a power of 100, that 2x plus 3 is one function, and then we would have x to the 100 as the other one? Sorry, you can't see that. Could you guys visually see that if we took this and plugged it in for that x, that's what it would look like?
Jaw.
Yeah? Okay, composite functions, one function inside of another. So if you want to write that down, that's okay. One function inside another. So that's something key for us to look for. If we can identify one function inside of another one, we're going to go ahead and utilize this shortcut called the chain rule. So how this works, we'll go ahead and write down a general statement, but then we'll apply it to some problems that I hopefully it'll start to sink in. Algebraically, we show one function inside of another one by like g of x inside the f function. Can you visually see how g of x looks like it's inside f, like you would plug it in? Okay. So this is how we find the derivative. I want you to kind of think, I think about Shrek all the time when I do this chain rule. Okay, remember in the movie Shrek, if you've seen it, he always talks about how ogres are onions. They have layers, right? Okay, so whenever you have a chain rule, when you have one function inside of another one, you have all these layers, or gobstoppers, one of my favorite candies, okay, all those layers of flavors and colors. We're going to keep peeling back the layers one derivative at a time until we get to the core, okay, the one that's kind of in the middle of everything. So if you take a look at the way this composite function is written, how would we represent the derivative of the outer layer? Do you see how f is on the outside? That's the outer function. How do we represent the derivative of f? F prime, okay? But if you take the derivative of the outside, you still have all of the other pieces on the inside of that onion or gobstopper. So we still have g of x on the inside. But now that we took the derivative of that outer layer, we're now going to move on to the derivative of the next layer, which would be g of x. We haven't taken the derivative of that yet, right? How do we represent the derivative of g of x? We would say g prime. Okay, so we're going to be multiplying all these together. We're just going to take derivatives of outer layers, peeling them away, and we're going to keep taking derivatives until we get to the one in the very middle. Okay? Let me do something a little bit more complicated on the board up here. Hopefully this would make sense. All right, let's say say that was our composite function. We have one function inside of another one, inside of another one, inside of another one. Can you visually see that? Okay, so if we were to apply the chain rule, we're going to take the derivative of the outer function, which would be which one? F. Okay, so if you take the derivative of the outside function, you still have all of the other ones on the inside. So all of those other functions are going to remain the same. Okay? But now that we took the derivative of f, we're going to move on to the next layer. So take a look at all the functions you have left. What is the next function that we haven't taken the derivative of yet? G. Okay? Now if we take the derivative of that, we still have all of those other layers inside of that one. Okay? What's the next function we haven't taken the derivative of yet? H. You see how we keep working our way into the core? Okay? So then we have H prime. And then what's the next one we haven't taken the derivative of yet? We have L. Okay? So this is a very complicated one because we have function inside of function inside of function. Okay, we're not really going to see examples like that per se. Maybe we'll have 2 or 3, okay, that we can think about. But the chain rule, I want you to think of like an onion or a gobstopper. You have all these different layers, and you're going to keep peeling them back one layer or derivative at a time. Okay, we'll see how this goes. It's a little different of a shortcut, okay, because we don't really have a phrase for it, like 1d2 plus 2d1 or low d high minus high d low. Okay, so this is just kind of a concept that you need to grasp in terms of a layer or a gobstopper. So let's see if we can do that here. Okay, let's apply our chain rule. If you were to apply a derivative to the outside, looking at how this is represented, do you realize how the power of 3 is on the outside of that function? Can we see that? So how would you take the derivative of something to the power of 3? Think about another shortcut. If you had x to the third, something to the power of 3, what would the derivative of that look like? We would bring the 3 down, and our new power would be 2, right? So that's the derivative of the outside piece, but we need to keep everything else that was on the inside, okay? All those other layers inside the onion and the gobstopper. So the 2x plus 3 really isn't being used just yet. Okay, that's the derivative of the outside. Let's move on to the next layer. Okay, so if we already accounted for that power of 3, we're now going to move on to the inside piece, which is 2x plus 3. How would you find the derivative of the inside, that next layer? The derivative of 2x plus 3? Just 2. Okay, do we have another layer to go into? Have we taken everything into account so far? Okay, so this is a 2-layer onion or gobstopper, not that crazy 4-1 that I did on the board. Okay, there's our chain rule. Derivative of outside, making sure you keep everything on the inside, you haven't touched those yet, and then you're just going to keep moving on to the next layer to find your derivative. So what we're going to do is we're going to clean this up, because technically this is the same equation we did at the top, so we should get the same derivative. Let's see if that's actually happening here. So we can combine the 2 and the 3 maybe to get a 6. And if you were to FOIL or distribute 2x plus 3, you get 4x squared plus 12x plus 9. And if you distribute in the 6, 24x squared plus 72x plus 54. Matches, right? Okay, so that means, let's go ahead and try the crazy one, okay? What if I changed it? What if I changed this to 2x plus 3 to the 100? Could we now find the derivative of that? We don't have to write it out 100 times anymore, right? Because we have this new shortcut. Notice how the power of 100 is on the outside? So if you were to find the derivative of something to a power of 100, wouldn't that be 100? And then what would your new power be? 99. Okay. We got to keep all the other inside layers because we're only doing the derivative of the outside. All right, so now take a look at the next layer, which would be the 2x part, or 2x plus 3. The derivative of that would just be 2. So what you could do is combine the 100 and the 2 together, but I'm not going to make you expand that 99. Okay, that would just be insane. But that is the derivative of 2x plus 3 to the 100th power. So now we have this shortcut to help us figure out the derivatives of these higher powered polynomials. Okay, so instead of having to write it out 3 or 4 or 5 times like we did previously, we can use a chain rule where we have these layers, like outer functions, inner functions. Okay, let's go ahead and try a trig one. Okay. Find the slope of the normal line if this was your function and that was your spot. Now there's kind of 2 different ways you can tackle this, and either one should produce the same result. There are kind of 2 ways we can rewrite this function, and depending on how you rewrite it, depends on the shortcut rule that you would apply. How can you rewrite sine squared? What does that technically mean? Yeah?
Sine theta times sine theta.
Okay, you have sine of theta being multiplied twice. Okay, that's one way you can think about it. Another way you can think about it, because it's a trig function, we kind of put the power in a weird spot, but you can think about sine squared as having one sine function raised to the power of 2. We can just put the 2 in a different spot. Okay? So take a look at this. Depending on how you want to rewrite it, it's depicting a different shortcut. If we have sine times sine, which shortcut would we use in that case? If you're multiplying 2 things together, we would use our product rule. Okay? But if you rewrote it like this, okay, do you guys notice or can you visually see how there are inside and outside functions, inside and outside pieces? You see how the 2 is kind of on the outside, whereas the sine is on the inside? If you can identify outside and inside functions or pieces, that's signifying a chain rule. Okay, so you have options depending on how you want to rewrite it. I know we're familiar with the product rule, and we could go through that and see how we would eventually get the same thing. But let's go ahead and just practice our chain rule, okay, because this is going to be kind of new to us. Okay, so we're going to try to tackle the derivative using the chain rule. What is the outer piece or function for that sine theta squared? The power of 2. So if you were to find the derivative of something to the power of 2, we would bring that 2 down, and our new power would be 1, right? That's the derivative of the outside, okay, the first layer of the onion, but we still got to keep all the other layers. We're not really touching those just yet, okay? We're just peeling back the first layer. So now that you're done finding the derivative of the outside section, move on to the next layer, okay, the next one that's on the inside. And the only other piece we have there is sine. What's the derivative of sine? We have cosine. So in terms of our chain rule, derivative in the end, we have 2 times sine times cosine. Okay, if you were to use product rule, you should get something that's exactly like that. You could test it if you wanted to. Okay, so there's our derivative shortcut using the chain rule. Let's go ahead and use it to find the slope of the normal line. Where do you guys want to go from there? I'm going to plug it in, 3 pi over 4. I see pencils moving, that means we're doing something. Okay, so 3 pi over 4, that's not in the first quadrant, something that we need to be familiar with. So if you need to reference the unit circle on page 10, you can. Sine of 3 pi over 4. And then we need the cosine value as well. Let's see, I think, is the sine value square root of 2 over 2? Is that right? Okay, and then the cosine value is the same but negative because we're in the second quadrant. Is that right? Okay, so multiplying those together, well, let's see, we're going to have initially the 2's, or a set of 2's would cancel, and then multiplying fractions straight across the top, we have square root of 2 times a negative square root of 2. The square roots would cancel, so we're just left with a negative 2. And we still have 1 2 left in the denominator. So it looks like we get negative 1. Is that our answer? We're shaking our head no. Okay, what does this negative 1 represent? Yeah. That's the slope of the tangent line. Okay, so slope of tangent means we got to figure out the opposite reciprocal, okay, the perpendicular relationship for our normal line, which would just in turn make it 1. Okay. All right, so in this section, we're just going to get used to identifying the chain rule. Okay, if we have outer pieces, inner pieces, how we can go through that derivative shortcut. Let's go ahead and check out some practice ones on the back. All right, so just as a reminder, you guys do have options here. Do you guys see that power of 3? You could write that quantity 3 times. You could go through that distribution process. And then you'd have to use the power rule to find your derivative, okay? But we now have the chain rule to our advantage to maybe make it a little easier instead of having to do all that simplifying. So can we identify the outer piece, the inner pieces, the layers of these onions and gobstoppers? What's our outer piece? The power of 3. Okay, so if you were to find the derivative of something to the power of 3, you would bring down that power of 3, and your new power would be 2. Okay, that's the derivative of the outside. We need to keep the inner layers, though, because we haven't touched those yet or taken them into consideration. Okay. So now that we're done with the derivative of the outer layer, let's move on to the next layer. It looks like we still have a 3x squared plus 2. So what would the derivative be of that next piece? We got 6x, okay? So there's the initial derivative using the chain rule. We can go ahead and clean it up. Maybe you want to do 3 times 6 to give you 18. And then the 3x squared plus 2 squared. Okay, that's one way you can represent it. Some of you may feel like expanding that power of 2, going through a FOIL process and distributing that in. You can do that, okay? I honestly don't know if this was a multiple choice question, what the result would look like. It may look like this. It may look expanded, okay, without the parentheses there. So you just got to get used to simplifying it when necessary. Okay, so if you want to leave it like that, that's fine, but realize you could keep going to get rid of those parentheses. All right, what about the next one for g of x? First off, can we rewrite it without the root? The square root's the same as what? A power of a half, okay? So this one is technically very similar to the one we just did, okay? Even though it started as a root, we can change it to a power. So let's tackle our chain rule, because we have inside and outside pieces. Notice how the 1/2 power is on the outside, so we're going to do that derivative first. We would bring down that power, and our new power would be -1/2. We got to keep the inner layers though. Anything that's left on the inside, we'll keep it. Now that we're done with the outer derivative, let's move on to the inner derivative. What's the derivative of 2x plus 5? We got 2. Good. So let's clean it up. We have a half times 2, which would just turn into 1. So we're left with 2x plus 5 to the -1/2. Instead of the negative power, we can make it positive by moving it to the bottom of a fraction. All right, so you could leave that as a derivative. Maybe you wanted to change it back to a root, because essentially that's what it started as. This would be 1 over the square root of 2x plus 5. Okay? They're all technically the same thing, they just look different, depending on how far you want to rewrite them. How are we doing with the chain rule so far? It's a little different. I know that, but we're going to get good with it with practice. What about the next one? Can we rewrite it? Get rid of the root? What would the power be? This one's a little tricky because there was a power on the inside too. How do we use that power as well as the cube root? What do you think, Justin? 2/3, good. Okay, so let's go ahead and use our chain rule. We have inner and outer pieces. The outer piece is the power. So if we were to find the derivative of a power, we would bring it down. And the new power in this case would be -1/3. We got to keep those inner layers though. Go ahead and move on to the next layer. What's the derivative of x plus 2? We got 1. So you technically don't have to write if you don't want to, because this is being multiplied. So if we clean it up, we can move the negative power to the denominator. Okay, essentially where that 3 is from the 2/3 out front. Alright, so you could leave it like that. Or maybe you felt like converting it back to a root. We would have the cube root of x plus 2 in the denominator. You're doing okay? Let's try another one. Let's rewrite the root. We have a 5 out front, and then we're going to rewrite the cube root, let's see, as a power of 1/3. Alright, so notice how we have inner and outer pieces. That means we can apply our chain rule. Let's see, our outer piece is that power of 1/3. So if you were to bring down that power, notice how we have the coefficient of 5 out front? So if you multiply down that power, the new coefficient would be 5/3. And then the new power, after we subtract the 1 from that power rule shortcut, would be -2/3. We still got to keep the inside layers. Speaking of the inside, what is the derivative of the inside, that next layer? Are you guys writing down 2x plus 2? Okay, good. let's see, if we clean it up, this negative power is going to move to the bottom with the 3. But up top, we still have a 5 times this other quantity of 2x plus 5. Or sorry, 2x plus 2. So you could leave it like that. Who knows? Maybe that's what it looks like on a multiple choice option. We can keep going though. You could distribute the 5 in up top. That's easy for us. And maybe you wanted to rewrite the fractional power as a root. Okay, we would have the cube root of x squared plus 2x. Okay, that whole thing squared. Yeah.
This is probably a dumb question.
Nope,
but
go for it.
For the 2x plus 2, would you be able to get anything out of that one? Like that layer, or would it just be 2x plus 2?
It's just 2x plus 2. Because this, I understand why you're saying that, but when you take a look at this inside right here, this section is not inside something else. We're gonna get there for the next one, okay? So far the ones we've been doing have just been double layers, okay, like you have an outer piece and an inner piece. We're eventually going to get into the next two where you might have 3 layers, okay, where you have to keep going a few times. Yeah.
Wouldn't that be 10x plus 10 because it's 5?
Oh, I'm sorry. Yeah, good catch. I just copied down the 5. Thanks. All right, let's take a look at maybe a triple layer one, what this might look like. So in terms of trig functions, I know they're tricky because the power is written somewhere different than when you're used to. But what we're going to do to help us visualize the chain rule is we're going to move that power to the outside. Something else we can do to help us visualize this is we can put the 3x inside parentheses as well. Because you guys seen trig functions with parentheses before. Whenever you type sine or cosine or tangent into the calculator, doesn't it always pop up a parenthesis afterwards? So usually there are parentheses there. Sometimes we just don't write them. So notice how can we, before we even start the chain rule, can we identify some layers? What's inside these other pieces? What's the outer layer? 2. The power of 2. Okay? So if you were to take that power of 2 away, okay, what would the next outer layer be? Cosine. Okay? And then if you were to take that outer layer away, you're left with 3x. Do you see how we have 3 layers? Okay? So we're going to have to do the chain rule kind of 3 times. Let's see what that looks like. Okay? So you identified the outer layer to be the power of 2. So we're going to bring down the 2. Our new power is 1. And we keep everything else, all the other layers. All right. The next layer you guys identified was cosine. What's the derivative of cosine? Negative sine. Okay. You keep the remaining layers that you haven't used yet, which would essentially be 3x. What was our last layer? The 3x. What's the derivative of 3x?
3.
Just 3. Okay, so that one was a little step up. We had a third one to do. Okay, if we clean it up, we have a 2 times a negative times a 3. All these are being multiplied together, so it'd be negative 6. And then we can write cosine of 3x and sine of 3x. I know we have a power of 1 there, but again, that doesn't really mean anything, so you can erase it if you wanted to. I don't want that to throw anything off for you guys. All right, so there's our final derivative after utilizing the chain rule 3 times. All right, let's try the next one. So for trig functions, we're going to move the power to the outside, because technically that's where it should be. We just don't write it there. All right, let's identify the layers. What's the outer layer? 2. If you were to take the 2 away, what would be the next outer layer? Sine. If you were to take the sine away, the next outer layer, or the next layer? 2x plus 1, both of those. Okay, so we have 3 layers. We're going to have to do 3 chain rules. Okay, so you said outer layer was 2. The new power would be 1. You don't have to write it if you don't want to, but we're going to keep all those other layers. The next layer you said was sine. What's the derivative of sine? We have cosine. We're going to keep the remaining layers we haven't used yet. So that would be the 2x plus 1. And then the last layer you identified was 2x plus 1, and the derivative of that would just be 2. Okay, all of that's being multiplied together. So we have a 2 times a 2, which would give us a 4. And then we're just left with those trig functions. Is it kind of starting to sink in a little bit? I'm thinking after we did 3 of them, that kind of helps, because you start to see the pattern or the process. Okay? We'll do more with the chain rule tomorrow, okay, because this one's a little bit different. We're going to spend some time on it.